Professor Mathur has, with her group, has led this line of research and quantified how much gas there is, and it looks like this is going to be important for not only just cosmological context, but also for galactic evolution, because it's a huge amount of gas. So she's going to talk about that today. I should also mention that recently she has been awarded a Distinguished Scholar Award from the Ohio State University in honor of this line of her achievement in her work. And I should also like to mention that Chandra, you also all know what Chandra Observatory is, the X-ray Observatory. They have invited, they're going to have legacy programs, legacy observations, and under that program, Professor Mathur is going to be the principal investigator for 2 of these legacy programs, which is going to take her to some other directions. But yeah, Professor Smita.
Oh, here. Okay. I don't need anything here. You can hear me. Okay, perfect. All right. Thank you very much for that kind introduction. It is overwhelming for me to be here. As Biman mentioned, I was a JAB student, and the first time I came to RRI was over 40 years ago. Well, that dates me, I know, but that's what it is. And, you know, we used to walk down from ISC for lectures here, and they used to be there in the building where the offices are. And there used to be some talks here which were generally given by big shots. And so it's very overwhelming for me to be standing here today. You know, I'm not one of those scary people, I should tell you. So, but I'm also very, I feel blessed that one of my JAB professors is here, Professor Malik here. I feel very overwhelmed because of that, and I do now spectroscopy for a living, and it is, you know, what I learned here from you has been with me all these years, and thank you very much. You know, I just realized this past Sunday was Guru Purnima, and I feel very honored that you are here today. Okay, so with that, let me start I left it here. With that, let me start with my talk. I'm going to be talking about the circumgalactic medium, as the title shows here. But I am a professor, so I'm starting with a quiz. Let's see how many of you students, maybe even faculty theorists, know which observatories are here. That? Okay, that's the Chandra X-ray Observatory. XMM Newton Observatory. That is Suzaku of JAXA. All these 3 are X-ray observatories, and I have used them a lot in my work. So grateful to all these people who build observatories and instruments and everything. We couldn't be doing our science without the enormous amount of effort that goes behind in making these observatories. This most likely most people know, which is Hubble Space Telescope. I have used Hubble for my work as well. I'm very much a multi-wavelength observer, but I will not be talking about my Hubble work in today's talk. And in a completely different line of work, but again related to the circumgalactic medium, we have also been using the Green Bank telescope, 21 centimeter observations to look at cold gas, which again I will not be talking about in today's work. It will mostly be focused on X-ray work because we are talking about the hot circumgalactic medium. So this is colloquium with not just for astronomers. Thank you for being here. And so let me start at the beginning. So we kind of know what the universe is made of. Most of it, 73%, is supposedly dark energy. Even though we don't know it is really energy. It could really be modifications to general relativity of this theory of gravity, maybe, okay? So 23% of it is supposed to be dark matter that we absolutely know exists, right? We have plenty of observational evidence to say that dark matter exists. But we do not know what that dark matter is. The constraints, observational constraints, are becoming narrower and narrower, and yet we do not have identification of dark matter particles. All right, but there is 4% are made of atoms, like things we all know and very much understand. And so we're like, okay, let's 4% it is, but at least we know that, right? So, but do we know how many atoms are there in the universe? And actually we do. In the high redshift universe, we can actually account for most of the matter that's there. And now on, when I say matter, I mean regular baryonic matter. No dark matter, no nothing, okay? Just regular matter that you and I are made of. That's all I mean when I say matter here onwards. So, in the high redshift universe, we kind of account for all the matter that's in the universe, and it is mostly in the intergalactic medium. We see it with Lyman alpha forest, all well and good, okay? But when we come to the low redshift universe, it appears that the matter is kind of missing on all scales. It is missing on the scale of the entire low redshift universe. So what I'm plotting here is, let's say here is the cosmic baryon to dark matter ratio, and this is what we have here observationally. It looks like that if you look at the entire low redshift universe as a whole, then we are missing some baryons compared to what we know are there in the universe. Then, if you come to much smaller scales, when the scales of galaxies, the building blocks of the universe, again, we appear to be missing a lot of baryons. Only in rich clusters of galaxies, that too like relaxed clusters of galaxies, we have close to cosmic baryonic to dark matter ratio. So there is this so-called missing baryon problem that has been with us for a while. And a solution to this missing baryon problems appears to be in this circumgalactic medium. But the reason to study the circumgalactic medium is not simply to find these missing baryons, though I must say that's where we started with. The reason for studying the circumgalactic medium has also to do with the entire science of galaxy formation evolution. So what this movie is from illustrious TNG simulations, and what this movie is showing you is the growth of structure in the universe. Okay, so here you are seeing much larger scale growth here. Here it is focused on one galaxy, and you can see the time is evolving from high redshift to lower redshift, and a galaxy is getting formed. The gas is falling into the dark matter potential well, and I'm going to move forward again. Like you're seeing here, we are come to redshift 1, and we can start seeing a stellar disk is formed. A lot of gas is still falling into, and stars are really there in the stellar disk. And I'm going to just basically end this movie somewhere around here. Now this is something very much like the galaxy that we know has now formed. But now I'm going to stop this movie here. Oops. Stop a little before. Okay, let's just stop it there. And what do we see? That yes, we have formed the stellar disk. That's the galaxies we see when we look up in the sky. They are there, bright, beautiful in optical light. But all the way, very, very far away from the stellar disk of the galaxy is this huge gaseous medium. right? And this gaseous medium is what is called the circumgalactic medium, because this is, to distinguish it from the interstellar medium, which is in the disk of the galaxy. That's the gas in between stars in the disk of the galaxy. That's we call the interstellar medium. This is beyond the disk of the galaxy, and that's why it is the circumgalactic medium. That's the nomenclature here. Okay?
Corona?
Yeah, go ahead.
Corona?
You can call it corona if you like. You can call it halo gas if you like. Yeah, the circumgalactic medium is a kind of a newly coined, by newly coined I mean 2 decades word, but yeah. So this is what is expected from theory, okay? Yes?
Yeah, so corona is the term that Lyman Spitzer used for the hot confining medium, and it is sort of the same.
Right. No, absolutely. And so, but I think okay, let's not go there, but I think there it was not all the way to the virial radius of galaxy. It was more what today we call extraplanar, but never mind. But those are small nuances. It is still circumgalactic medium. So this is what the theory is telling us, that there is a lot of gas. As we can see, the gas over here is instrumental in formation of galaxy, as we just saw, and therefore in order to understand galaxy formation and evolution, it is very important that we understand the circumgalactic medium. It is the circumgalactic medium where the missing baryons are supposed to be there. It is the circumgalactic medium where missing metals are also supposed to be there, which I'm not going to spend time discussing. But basically, this is just to say this is a very important area to study, okay? And that's what we have been trying to do. So once again, to define CGM, or the circumgalactic medium, is the gas filling the dark matter halo of a galaxy. And then, what are the properties of this gas, right? So the virial temperature of a galaxy like Milky Way, like an L-star galaxy, is of the order of 1 million degrees. 2 million degrees of that order, right? So it's really hot. Okay, so how do we study this hot tenuous medium? How do we find these missing baryons? This has been with us for a while, and that's what we are trying to study. This is just a snapshot similar to the snapshot of the movie. Here is the teeny stellar disk, which is filled with halo. If you focus in on the stellar disk, it's actually pretty dynamic region here. There are outflows coming from the stellar disk, the so-called feedback, and then the gas goes up, it can cool down, fall back, and then aids into the star formation, and this is a dynamic system over there. And this interplay between the stellar disk and the circumgalactic medium, and also somewhat intergalactic accretion, kind of defines the way a galaxy forms and evolves. This is what I have been trying to say. And so the question now is, how do we study it, right? So because of our special vantage point that we are actually living in the Milky Way, most of the work that we have done is focused on the Milky Way CGM. And we had done it both with absorption line spectroscopy as well as looking for emission from this circumgalactic medium. And then I will talk a little bit about the E Rosetta bubbles, which is a special structure at the center of our galaxy. Then I will talk somewhat on pushing our work to external galaxies, and this again we have done both in absorption and emission, and all of this is with X-rays, okay? But there is an alternative to X-ray observations to see hot gas, and that is doing Sunyaev-Zeldovich effect, and we had done that too. And this is maybe a good point to plug in work of my former student Sanskriti Das. I'll be citing Das et al. Papers a lot in this talk, and she has worked on all these 4 things, which is why she has been an amazing student. but to combine all this and get insights into the physics of what's going on, we also need theory and simulations. And I'm very delighted now Manami has joined our group and helping us with theory. And now I'm also working with your student, Mukesh here, and I'm very happy to be talking about their work as well. So this is basically what we are going to be talking about. Yes?
Something about this dark matter potential well. So the gas that is confined by that dark matter potential well.
Correct. That's exactly the idea. Yes.
Because that matter, they will also have mass, right?
Yes,
Like,
but that is insignificant.
okay.
Very insignificant compared to the mass of the dark matter halo. The baryonic mass in the typical galaxy is of the order of 15%. So it is insignificant, and yet baryons are what we have to handle. Yeah.
Thanks.
Yeah. All right. So let's move on. So how this is like million-degree gas is called warm hot for some technical reason. Don't worry about that. We are basically talking about the million-degree gas here. So how do we detect that, right? It's too diffuse. It's supposed to be too diffuse to have significant emission, making this very different from clusters of galaxies, which are like bright X-ray sources. This is not. It's very, very tenuous gas, very difficult to detect in emission. We do detect it nonetheless, but I'm just saying it's a very hard thing to do. And so in this, hydrogen is fully ionized, and therefore we can't see it in absorption line spectroscopy with Lyman alpha forest as we saw at high redshift. And most of the other metals are also very highly ionized. And so one of the good ways to look at these million-degree gas is looking at the absorption lines of abundant metals. For non-astronomers here, metals for astronomers mean everything other than hydrogen and helium. So oxygen is a metal, sorry, but that's what it is. And basically, we distinguish elements on whether or not they have been generated through nucleosynthesis in stars. They are metals. Hydrogen and helium are not generated in stars. They are primordial, so they are not metals. That's the distinction. So yes, everybody, oxygen is a metal for this talk. So they are highly ionized, and so we can look at them. So 6-time ionized oxygen, astronomers call them oxygen 7. 7 times ionized oxygen is oxygen 8, and we can look for transitions of these ions to look for this million-degree gas, and that's exactly what we did. And this is where the X-ray advantage comes. This is where it is necessary for doing X-ray observations, because the most important transition of oxygen 7 lies at 21.602 angstrom. That is solidly in the soft X-ray band. Similarly, for oxygen 8, it is 18.9 angstroms. You know, first time in astronomy, in the X-ray band, we actually talk about wavelengths. And this has happened because Chandra and XMM Newton carried gratings on board. So this has been absolutely transformative in doing X-ray astronomy. Without gratings, we couldn't do the kind of work that I'm going to be talking about. And today we are celebrating almost today, July of 1999, 25 years ago, Chandra was launched. And so this work, the whole field of the circumgalactic medium and all the hot circumgalactic medium was created, has been created, and continued to grow because of Chandra and XMM. So that's a big, big tribute to these observatories. Of the order of 250 kilometers per second. Yeah. So it's not huge compared to optical high resolution, but from X-rays, where we typically have CCD spectroscopy, it is a big deal. Yeah. And so, of course, this is oxygen. In principle, you could have the inertial transitions of highly ionized other metals also, and we could see that, and I'll be touching on that a little bit more. And so, as I said, the first decade of observations with Chandra and XMM was amazing, that this is the kind of spectra we saw. Wherever we looked at extragalactic sightline with high signal-to-noise spectrum, boom, right there at 21.62 angstrom, we see an absorption line. And this was super exciting because this is like, wow, there is hot gas. Okay, there's no question, that's what it is, and we see it. And we could see some other lines also. We can see oxygen 8, but you know, oxygen 7 line is beautiful, and everywhere we saw the first decade of observations with Chandra and XMM. This was the kind of papers we used to write, that, oh, look, we see oxygen 7 in this direction, we see these ions in that direction. It established the fact that the hot gas around the Milky Way exists, though we didn't know much about it then. What about emission from this gas? So back in Rosette times, people had discovered the soft diffuse X-ray background. And here is the map of the soft diffuse X-ray background from Rosette at 3/4 of a keV, which is where a lot of oxygen emission comes from. But the Rosette did not have the energy resolution to actually separate foregrounds and backgrounds and the CGM emissions. Just didn't have the capacity to do that, okay? And only after I started working on this, I realized how messy the soft diffuse X-ray background is. It has contributions from things like solar wind charge exchange. And I'm like, I'm an extragalactic astronomer. What do I know of solar wind charge exchange, right? So this is very messy, and therefore separating out these foregrounds and the cosmic backgrounds and actually extracting the spectrum of the circumgalactic medium has been a very messy thing, very complicated thing, and something that could not be done with Rosette. And this is where XMM Newton helped, and Henley and Shelton did the heroic job of separating these out and actually producing the maps of the Milky Way oxygen 7 and oxygen 8 emission here now. And now we know that, yes, there is both absorption and emission coming from the hot plasma around the Milky Way. And so now we can actually figure out its physical properties, which is what we actually did. So when we actually look at absorption lines, basically what we measure is column density, which is a product of density and path length. But when we are looking at emission, we measure what is so-called emission measure, which is a product of density square and path length. So if you have two equations, two unknowns, we can solve them, and which is exactly what we did towards the end of the first decade of observations, when we really had observations of a lot of many sight lines with Chandra. And this is what we did, that looked at many, many directions, looked for observations of detections of oxygen 7, and this is what led to our first breakthrough in terms of understanding the circumgalactic medium of the Milky Way, that we found that it is truly very, very extended, okay? At least over 100 kiloparsec, very clearly, almost certainly going all the way to the virial radius of a galaxy, which is over 200 kiloparsec. So we knew that. We calculated the density, which is really small. Again, happens to be something expected from theoretical grounds. And then we could calculate the mass in the circumgalactic medium, which is over 6 times 10 to the power 10 solar masses, which is more than, comparable or more than the entire disk of the galaxy, including all the stars and the interstellar medium. So this was fun, obviously. And again, like this could be done because my then postdoc, Anjali Gupta, her expertise was with the soft diffuse X-ray background. So we knew how to do that messy separation, so foreground and background. But a lot of early works on this really got wrong results because solar wind charge exchange wasn't taken into account properly. Yeah.
Mass is 10 to the 11 in the disk of the galaxy.
No, it is of this order. It is of about, like, even if you add interstellar media.
10 to the 11 is the stellar mass in our galaxy.
That's why.
Huh?
I wanted to speak in the mic because we're live streaming.
Oh, I see. Oh, yeah. No, stellar mass in the disk of the galaxy, our galaxy, 2 times 10 to the 11. It's this is lower than that.
Okay, maybe. I thought it is of this order, but
No, it's 2 times 10 to the 11
there is
mass of the galaxy.
There is a clear factor of 2 difference in the total mass of the galaxy because we don't know how much that exactly the gravitational mass of the galaxy is, but I thought stellar mass is of this order. But anyway, I'm not going to worry about factor of 2s here. It is clearly going to, it is showing you that it is of the order of the entire disk of the galaxy, something that we had not seen before at all. So that's the point I'm making here. So this work led to this. So from this first few minutes of my talk, the takeaway is this figure, okay? So this is what, if you remember, as to what Smita talked about, is this, that this is where your stellar disk is. These are the Magellanic Cloud. Here is the virial radius of a galaxy, and it's filled with hot gas with comparable mass, which is diffuse, very low density. It's hot of the order of million degree and very massive. That's the takeaway, okay? So now I'm going to take you a little bit fast forward, and eventually we are basically moving beyond finding the missing baryons. Kind of looks like, okay, they're there, okay? Maybe factor of few something, 10 few percent, we are not going to worry about so much. There are baryons there. Let's try to characterize this more, understand the feedback, feeding, understand galaxy formation, evolution. That's where, in general, we are moving towards. But now I'm going to skip a few years in the work and move to this work. A very, very deep observation of a background quasar with XMM Newton, okay? So this, close to 2 megaseconds of time with very high signal-to-noise spectrum. The reason we got this time because we were looking for the elusive wormhole intergalactic medium, which is a separate talk. I'm not going to be discussing it. But I knew that this is going to give me an exquisite spectrum of the galaxy, absorption lines from the galaxy. So it is, okay, so it is an exquisite spectrum. And I look at it and I'm happy, yeah, sure enough, I'm seeing the oxygen 7 absorption line, I'm seeing the oxygen 7 absorption line, and I look at this and you want to start jumping up and down. And the reason you want to start jumping up and down is not only that you see oxygen 7 and 8, you actually see neon 10 line. This is the first time a neon 10 line has been detected, right? And it is immediately telling me that I'm actually looking at a hotter gas component, which is not million degree, okay? And there is also neon 9 and this neon 10. Okay, so this is great, exciting. Then I look at the spectrum again, and I want to jump up and down once again. Why? Because I realize that, oh, look at the strength of the neon 10 line. It is as much strong as oxygen line, if not maybe more. And obviously the neon abundance is way less than oxygen abundance, and if the lines are equally strong, it is suggestive of there somehow being overabundance of neon, right? So this is very exciting, but Abjad doesn't publish me jumping up and down, so we actually have to do some work and write the paper, and that's exactly what Sanskriti did. So here is our first result from this amazing spectrum is the discovery of a hot component, hotter than the million degree. This is now close to 10 million degree gas component. And here is the details of the spectrum. Here is the normalized spectrum. Here is the neon absorption line. The color here, our green straight line is the 10 to the power 7 Kelvin, and the dotted line is the 10 to the power 6 Kelvin gas. And this has been done. Models have been made using our ionization code. This is gas in collisional ionization equilibrium. And you can see for to explain neon 10, you essentially need only the 10 million degree gas. The million degree gas contributes nothing. On the other hand, if you look at oxygen 7, most of the absorption line has been explained by the million degree gas, and 10 million degree gas is contributing nothing. But if you look at other intermediate ionization state like oxygen 8 or neon 9, there is some contribution from 10 million and some contribution from million degree gas. And so very good detailed work that was done. This is the first result from this work. And the second, as we said, is that neon appears to be overabundant compared to oxygen. And again, this is now models on the spectrum here. Here is the neon 10. The purple line is what you would have seen if neon to oxygen was solar. And the yellow line is what you see when a supersolar neon to oxygen. It is of the order of several times solar. And you can see that with other elements as well. And then we realized there was actually yet another very interesting result coming from the spectrum, which I couldn't just see. And that is non-detection of iron. Okay, so non-detection here is important because what is showing here, if the yellow line is if neon to iron was solar. If neon to iron was solar, we would have seen strong absorption lines of highly ionized iron, which we do not see. So neon to iron is also non-solar. So these are all very interesting results because they were not predicted by any theories that time when we first published this. Even though all the simulation suits have happened, nobody looked for very hot gas. Nobody cared about metallicity just because there were so many other things to do, right? So this was fun. And of course, then the questions are, are we really seeing alpha enhancement? Is it really from the output from the coal collapse supernovae? Why are we seeing supersolar nitrogen to oxygen? Is it because of AGB star output? All these very interesting questions. But I don't want to jump onto these very cool conclusions because there are other possibilities, right? In principle, what we are observing is something very local, that there could be inhomogeneous mixing, and there could be, because, it's not that the neon is overabundant, but maybe oxygen is underabundant because of its cooling. And there are these other options that we need to consider before jumping on to talking about nucleosynthetic yields. Anyway, so then we could also look for emission around the cycline where we see absorption, and we found something very interesting here, is that here are the temperatures, the million and 10 million degrees that we had seen in absorption, and here is the two temperature regions that we saw in emission. We again, we clearly now see that even in the X-ray band, the circumgalactic medium appears to be multi-temperature. So there is a range of temperatures here, and this is what these works have told us. And this led to now the 2020 press release from European Space Agency, because this is the XMM Newton work done. So instead of one color of the circumgalactic medium in the previous press release, now we have a multicolored circumgalactic medium to depict its multiple temperatures, and all these different dots are kind of symbolic about the different ion ratios. Okay, so of course, we looked at this, that was just one sightline, right? However exciting it is, we can't really draw conclusions about the entire Milky Way CGM looking at just one sightline. So obviously, we are looking at other high signal to noise spectra. And indeed, we do see that in other sightlines also, as we saw. Here is one more sightline where, in addition to the kind of virial temperature, we definitely see again neon 10, and there is also carbon 5 absorption suggestive of like sub-virial temperature. So yes, it is multi-component, multi-temperature distribution gas that we are finding, and we again see null solar abundance ratios and alpha enhancement. So this is seen to be a generic property, at least in the few cyclones that we have seen. We are doing more work is possible in emission, and I'll be coming to that in a bit. So this is one cyclone where we have studied the emission around an absorption cyclone. And again, we see clearly two separate components of temperature, virial temperature, supervirial temperature, and the size of the circle is proportional to the emission measure, so how bright they are. And we see here on the scales of order of degree, we see actually inhomogeneities, most likely caused by density inhomogeneities. Again, for the first time, we could see that in our CGM. But there is a very interesting thing here which was puzzling, okay? So we see here in this particular cyclone, here is the absorption temperature, a few times million degrees, and this is the few times 10 million degrees, the hotter component. And these dots line are the different fields where we have emission, okay? And I was like, fine, they don't have to be the same, but can we understand them? Now this difference we can understand, because if oxygen 7 is mostly at this temperature, we can see more absorption here, but the emissivity of oxygen 7 actually peaks around here. So you can expect to see emission at that hotter temperature. So that's fine, but this was harder to understand. Why am I seeing this lot of emission in this temperature region? This was puzzling, and I couldn't let Josh submit this paper till we really understood this. And so what we did is what I called chemical tagging. We went like element by element and produced the kind of spectra they would generate for our temperature ranges, and saw what kind of spectra they are basically producing. I mean, this is where oxygen only, neon only, and we kind of kept chipping at our data to find out what our spectra are actually showing. And what we found is that the hot component, the 10 million region around there, the component that we had seen, is really driven by L-shell transition of highly ionized iron, iron 17 to 22. And so here is something very interesting. In absorption, we did not see iron. There was non-detection of iron. In emission, we are seeing mostly iron in the hot component, at least. And so that is already telling you these are different things, right? Chemically, we are separating these regions out. So basically, all these different observations that I'm talking about have the potential, really, to provide us with the chemical enrichment history of the intergalactic medium, the thermal history, the circumgalactic medium, and the thermal history of the circumgalactic medium, playing a very important role in galaxy formation evolution. And that's basically what we are going to. But obviously, a lot of detailed work we'll continue to do in terms of determining ubiquity of these parameters and ubiquity of these different components. And I'll come back to, again, ubiquity in all sky maps soon. But for now, that's what I will, this is where I will leave it for the overall Milky Way's CGM, basically talking about what is the structure of the CGM, where are all these regions there, right? So what is the distribution of the different phases? So if this is the stellar disk, you can imagine there are supernova going out, and that's heating up the region around it. So is it there that around some extraplanar region you have the emitting hot gas? Is it that around it you have the emitting warm hot gas? Is the absorbing hot gas beyond that? And is the absorbing warm hot gas filling the halo beyond that? That is a possible geometric thing. And in fact, this is the geometry that we investigated with Mukesh's work, and I'll be mentioning that in just a bit. But it need not be the case, right? It could be something completely different, that the density is coming from, emission is coming from clumpy, denser regions, and absorption coming from more tenuous, extended region. Understanding these and disentangling all these things is the work that we'll continue to do. And coming back to Mukesh's work is in Joy Bhattacharya's paper, we had seen actually that the emission measure of the million-degree gas and 10 million-degree gas is correlated, okay? And by the geometry that was derived, the kind of geometry I just mentioned, this correlation comes very, very naturally. That's showing us that the emitting gas is likely extraplanar. And then Mukesh went ahead and actually did simulations with injecting energy in the disk of from the disk of the galaxy through supernovae. And this is, what he found, that you can very easily see an extraplanar region formed with very hot temperatures. Around that, you have a region formed, which is extraplanar region with million-degree gas. The metallicity is plotted in the bottom right curve here. You can see very high metallicity gas in the hot regime. It can have a lot of iron, but maybe not in the region around that. So it's very suggestive and very interesting, but Manami says not so fast, okay? So here is some work that she has done with fire simulations, and here is her temperature and radial distribution of the hot gas plot. And if you kind of make a line here to show this as our super hot gas, super virial temperature, you can see it is also coming from about 10-20 kiloparsec from the disk. So again, extraplanar, but interestingly, in this simulation, you can generate this even when there is no feedback from the stellar disk. So the question is still there, but I often say that it's astronomy. So when the question is it A or B, almost always the answer is yes, because both processes may be important at maybe different times, or at maybe different galaxies, or in different environments. So obviously, it's all very fun thing to do. We'll also be looking at the illustrious TNG simulations with another student. We clearly again see very hot gas here in the temperature density phase space in these simulations as well. But these are for more massive galaxies, and these are for less massive galaxies. For Milky Way, I still have this number here, but anyway, factor of 2 different from yours. But anyway, we will be working on getting these things through and trying to get insights from different simulations as well. Now, quickly move on to external galaxies. This is obviously very difficult because they are far away, so very faint, and you have to get a very right setup to be actually successful. And we were successful by choosing a very, very well-defined parameter space. And it just so happens that this galaxy in GC 3221, even now, after a few years after we published this, is still the only Milky Way type galaxy in which circumgalactic medium could be detected for various technical reasons, which I won't get into. So this is the surface brightness profile from the center of the galaxy. You can see clearly the emission saturating out to the background region, showing you that the CGM has been detected in this galaxy. This was done with Suzaku. The first discovery was done with Suzaku observations. Subsequently, we also confirmed that with XMM Newton observations, and we find that the gas in this external galaxy, CGM, is also enough to account for its missing baryons. So that has been pretty gratifying. And another interesting thing we found with XMM is for the first time we could measure a temperature gradient. The gas is not isothermal. There are big error bars, so obviously it's not like something we can make out of it, but definitely that's suggestive. And so if it is not isothermal, then we can do some fun things. We can try to figure out what the model would be. Is it really the hot gas in hydrostatic equilibrium in the potential well defined by the typical, what is called the NFW profile, galaxy's dark matter potential well? In that case, these are the kind of temperature and density profiles it would have. And so, okay, let's look at our data, try to fit it. And sure, you can fit it, big error bars, but you get some numbers which are reasonable, but, it's nothing very, very constraining as such. And therefore, we have now gone ahead to get very deep observations of these galaxies with XMM Newton, and Sanskriti is reducing those data as we speak, and soon we will really know whether we are really looking at CGM in hydrostatic equilibrium in the dark matter potential well. So that would be a fun new thing to actually find out. Now, external galaxies in absorption, this is even more difficult because galaxies are not necessarily aligned in the sight line to background bright X-ray quasars, just so that I can observe them, so making it even harder, right? But so we, again, chose very wisely, and yet the signal was very marginal in this particular galaxy we looked at a given particular redshift in the sight line to a quasar. So very marginal, that's what we say. But here we have a very clear, absolutely robust detection of oxygen cement absorption line here. This is the same redshift where oxygen 6 and Raman alpha absorption exist from Hubble data towards a background, in the sight line to a background quasar. And so this is now a CGM of a galaxy of redshift 0.225. And we can again, and it has an impact parameter of over 100 kiloparsecs. So this is cool, right? Because, when we are in our own galaxy, measuring its size of the CGM is hard. But when it is external galaxy, I can actually measure how far it is from the center of a galaxy, and 116 kiloparsec. Yes, that is CGM. So it is extended, it is diffuse, it is massive. So even this external galaxy work actually gives more credence to our work of the Milky Way. So it's been all hanging in together very nicely. All right, so this is all the work on the CGM that we talked about. And because in the interest of time, I won't go through the summary and go to something else which really actually fell in our lap while not looking for it. Okay, so here are the E Rosetta bubbles. And this is a figure from the 2020 Nature paper by Pradel et al. So here is the galactic disk. Here in red are the Fermi bubbles, which we knew for a long time. And what E Rosetta discovered are these blue things. So this thing we already knew, the North Galactic Spur. The real discovery was this lower part, which is fainter, but then that connects with the northern part and tells you that you actually have X-ray bubbles at the center of our galaxy, in addition to the Fermi bubbles, which are discovered in gamma rays. Okay? And like everybody else, I also looked at that paper and like, oh wow, and never thought I would ever write any paper related to this, right? But so we were doing our own job, minding our own business, looking at the CGM all across the sky with Suzaku and looking at the emission from the circumgalactic medium. And we had over 200 cyclones, okay? And so we plotted it all across the sky, and our job was to look for, again, how ubiquitous this hot component is. And we found it to be there everywhere. In, I think, over 80% of the cases, we found hot gas, so pretty ubiquitous. But then we also realized, as we plotted it like this, that a lot of our fields were along the shelves of the E Rosetta bubble, and of course we had the fields which are around rest of the sky, right? And I'm like, okay, so let's look at that and compare the two. And this is what we found. Okay, so these are the distributions of thermal parameter. This is now the warm, hot, virial temperature gas, and this is the the galactic L values. Okay, so this kind of shaded region here is the galactic center area where the bubbles are. And what do you see? The temperature is not different in the shells, in the E Rosetta bubbles, or outside. And sure, the bubbles are brighter, so you see a clear jump in the emission measure. So they're clearly brighter, that's why they stand out, but they are not hotter. Okay, and why is that important? I'll come in just a second. They are obviously brighter, but they are not hotter. And this is like jumping at us. We are not looking for this. And the same, as I said, we also discovered the super hot component. Again, there is not any significant difference at the E Rosetta bubble region. If at all, it's maybe slightly less, but definitely not more. Again, there is higher emission measure there. They are brighter. So what does this tell us? That these E Rosetta bubbles are not shock heated, because there is no heating, the temperature is the same. But shock heating was the model that was there in the Discovery Nature paper, and we can't really agree with that there is no heating happening there. So they are bright because they are this compressed, denser gas, but they are not bright because they are shock heated. So what exactly is the shock properties? I've been talking to Biman and Pratik about it, and maybe we'll figure out something, and that would be a fun thing to do. So this is, as I said, something that we were not looking to do, but was a fun paper to write. So basically, we were very lucky to be making interesting discoveries, and now we are trying to take it as far as we possibly can. Where is the hot gas, how ubiquitous it is, how exactly it is related to galaxy formation evolution, what's the theory behind it, all those things that we are looking at. We will try our best to give the most comprehensive phenomenological model of the Milky Way circumgalactic medium, accurately determine baryonic mass. We are pushing more for the similar work for other external galaxies. And we definitely do want to do is connect the properties of the circumgalactic medium to the properties of the stellar part of the galaxy also, because this is where the degeneracy between various theoretical models might break. Okay, so a lot of models of galaxy formation and evolution are fine-tuned to explain the properties of stellar disks of galaxies, but they are degenerate in many other ways. And so how do we break these degeneracy? How do we choose a model? And so theorists have agreed that maybe the great way to break the degeneracy is really look at the circumgalactic medium. So we have the opportunity to actually potentially do it, and we'll try our best to do that. Thank you very much again for inviting me. It has been a pleasure. And I'll just leave here to review articles that I wrote, which might, some of you students might find useful. Thank you.
Very nice questions. If I were to plot the density of the baryonic matter from the center towards the edge of this cloud, is there a very clear-cut boundary where, I mean, you think something the density falls off very sharply at the edge of the galaxy, or is it like a continuous?
I cannot answer that question for our galaxy, but I can answer that question for the external galaxy. For our galaxy, because we are in it, it is very model dependent. I mean, I can make a model and I can give you a number, but it won't be very, it wouldn't carry much weight. But for external galaxy, yes, we clearly see the surface brightness profile I showed you. It was the beta model profile, and it goes to the background. So you see a boundary, but that is not necessarily the boundary at which the circumgalactic medium ends, because that boundary is an observational boundary, and it is determined by where the background is. If I had didn't have instrumental and cosmic background, and if that was lower, it could have gone further. So this is an artificial boundary, not real boundary.
And my second question is that I was curious to see that in the artist rendition of these clouds, it's shown as isotropic, even though the galaxy itself doesn't have that symmetry. Is this because, I mean, are these like some sort of convective clouds which is around the galaxy, and therefore because the galaxy is what is hot?
Yeah, so if you are referring to the first artist rendition, we have reasonable evidence for that. I'm not sure which artist thing you mentioned, but if it was one of the first slides, then we have reasonable evidence for.
I think this one, for example. Yeah.
So this one, it is just showing a cloud. Nothing more. But if if you're talking about this, then we have pretty good evidence for outflows, like in M82, you see a lot of good amount of outflow, you see things falling down, there is evidence for that. So we see some activity happening at the centers of the galaxies with starburst-driven superwinds. But those are special cases. But even when you don't have superwinds, you do have winds.
Thanks.
Yeah.
Sorry, it's a very basic question. In our galaxy, when you detect this hot gas, oxygen 7 and oxygen, what is the background source to see the absorption? These are
a quasar, a blazar in particular. Yeah, and they are bright in X-rays. We like to choose blazars because they have don't have any intrinsic feature. They are featureless continuous, so don't have to worry about it. Having said that, some of the sightlines we have now looked at quasars. They have their intrinsic spectra. Right. We have to worry about various. Anyway, yeah, blazars are good, but they aren't enough.
Okay.
Yeah.
Thank you.
So the external galaxies for which you have data, can you say something about the profile of the absorption lines vis-a-vis the systemic peculiar velocity or?
Yeah, so there is delta V. There is some difference at the exact redshift of the galaxy as determined by, not sure anymore, but there is I think maybe Balmer break or something. But anyway, you have the redshift of a galaxy, and you have a redshift of other absorbers with some impact parameter from that. And I think that delta V is of the order of like under 100 kilometers per second, though I don't remember the exact number.
Oh, okay. So it's similar to the dynamical.
Oh, exactly. And it is exactly the same as other absorption systems. But there is this small difference with the systemic redshift of the galaxy and the absorber velocity.
So indicating inflow?
Or outflow.
Okay.
I have two questions. One is with this baryonic mass estimate for the CGM of Milky Way, that's comparable to the galactic disk mass.
Yeah.
So you still have the problem of missing baryon at larger length scales?
Larger, oh yes, I mean you in the intergalactic medium, oh yes, we
That's
still
it.
have the intergalactic medium missing baryon problem still exists. We have a few papers where we have talked about detecting possibly detecting lines from the intervening material, putatively from the warm hot intergalactic medium, but I think thinking more about it, it's becoming more and more clear to me, and that's what I also say in the review article, is that whatever the lines that we are detecting, most likely are associated with intervening galaxies rather than the truly diffuse intergalactic medium. And again, you might ask, what it is, oh, it is a matter of semantics, like where is the galaxy and where is the intergalactic medium? And I will make the distinctions really in terms of density. You know, if you're going significantly below 10 to the power minus 4 per centimeter cube, then maybe you are in the intergalactic regime, and if it is, you know, of this order of 10 to minus 4, then you are in the CGM regime. But the probability of detecting these very high column density systems that we detect with Chandrayaan XMM, that arising from IGM is very, very small. It would be tip of the iceberg. So that's why I don't think it is truly IGM anymore.
And this gas is being enriched by the galactic outflows.
Yes.
So the metal, what is the kind of time scale for that? The metal abundance in the CGM is then likely to be less than the galactic metal abundance?
Absolutely, yeah. So
if
it is,
you are-
yeah, so, you know, again, it's very difficult to measure exactly because we don't have any, so to know metallicity, we need to have hydrogen, and we don't have handle on hydrogen because in the X-ray band
So
we
in
have
the-
no hydrogen. So, but it can be, it is roughly measured, and it is of the order of, and at least the theorists tell us it's of the order of 0.2 plus or minus 0.1 solar. So 0.1 to 0.3 range.
No, so when you are doing the mass measurement of the baryonic component from the oxygen lines,
We have
assumption-
assumed
that
it is
assumption
0.3.
goes into it. There is a
Yeah.
factor of uncertainty. It could even be on the higher side.
Correct, yeah.
So you were talking about these two temperature components. One is at million and the other is at 10 million kelvins, right? So do you have separate estimates of the metallicity for these two components, or?
Again, we don't have any estimate of metallicity, but we have estimates, measurements for abundance ratios. Metallicity, by definition, is with hydrogen, and we can't do that. But we have abundance ratios of neon to oxygen and nitrogen to oxygen, or neon to iron, and those. And yes, they are different. We have different estimates for the million degree and 10 million degree, which how exactly different they are, I don't remember. But there are few factors of few different.
Okay, and is it a significant factor that you have a degeneracy in your normalization of your epic models and your metallicity? Is this a problem, or how difficult is it?
This is a great question. Temperature is measured robustly.
Okay.
The degeneracy with metallicity is only with the emission measure.
I see.
And it is not with temperature. Yeah.
Thanks.
Just a curiosity question, what are L-star galaxies and how is it different from normal galaxies?
Okay, L-star is a normal galaxy, but the thing is, how do we define what is normal, right? We can't just say a Milky Way-like galaxy is normal galaxy just because it's our galaxy. So astronomers have a way of defining what is normal. And there are different people do it different way, but one of the ways to do that is plotting what is called the luminosity function of galaxies. That means yeah. So a luminosity function of galaxies is basically number of galaxies per unit volume, per unit luminosity, let's say, and you plot it as a function of luminosity. Then this function has a typical form, which is kind of goes like this. So it has a knee, and that is L star. So, and this is where Milky Way lies as well.
So you said the Rosetta seems to be not shock heated. Is there clarity on the Fermi bubble on this?
No. There is a big debate going on. Big debate is also there in terms of how Fermi bubbles are created, in terms of whether or not it is some activity driven by AGN, or is it star formation driven activity like supernova driven outflows. So that debate has always been there for Fermi bubbles, right? And that has always been there. And now we have the same debate now also for the E Rosetta bubble. And there are reasons for us to think maybe it has to do with star formation driven activity because of the kind of abundance ratios that we see. They look more natural to come if it is from star formation driven outflow rather than a jet from the AGN. But again, I guess it will depend. The answer would be depends on who you ask, and some people have their favorite things. I have no favorites. I'm good with everything.
Thank you.
If there are no more questions, then let's thank Smita for the wonderful, thought-provoking talk on hot gas on a cold day here. Tarun, would you like to do the honors? So this is a small token of appreciation from RNA.
Oh, wow, thank you. Thank you, everybody. Thank you. Oh, wow. Oh, okay. Thank you.
This has been a question about why we take pictures. I just attended a telecon before I came here, where we were told that RNA is doing well, but the minister prefers 100 times more.
Whoa. Okay, you can take 100 pictures. Thank you. Thank you, everybody.
Is that the second edition of the
Yes.
Victoria?
You don't have a
No, I want to